Good afternoon, everyone. I'm Thomas. I'm presenting to you from Ghent here in Belgium. And today I'm talking about post-fire damage quantification of concrete tunnels. And for that, we, of course, use SAFIR. Starting with the introduction. The picture you see on the slide now is basically a picture of the city of Antwerp here in Belgium. And this green ring around it is basically a future vision that some people have for the city, where they want to move the entire ring road underground. In our parts of Europe, where everything is quite flat, and where space is limited, this is sometimes a nice idea to create nice new green spaces. It is a future vision. It's not yet there. It's also a very costly solution, but there is already definitely many examples of these kind of tunnels being built. So the focus of the presentation today is on tunnels which are what I call shallow tunnels or cut and cover tunnels. So not the tunnels you typically find in the mountains, which more have like a circular cross-section. I found the literature already quite some research on that, but these shallow tunnels have been studied not so much. So the main research question today is how do shallow concrete tunnels perform in case of fire? We started this project after a question from a client, and we actually studied already now 6 of these types of tunnels as part of a project for Rijkswaterstaat in the Netherlands. This project consisted of 3 parts. The first phase is already a long time ago, where we did a cost-benefit analysis to see what is the most efficient way to protect the tunnel. Can be passive fire protection, can be sprinklers, or can be not doing anything at all. The second phase is where we actually analyzed for these different tunnels, how do they behave in fire? Do they collapse? Do they not collapse? If they collapse, do they collapse after 50 minutes or after an hour? And today I'm really focusing on this third phase, which is the post-fire damage quantification, and also already looking ahead a bit, also looking at repairability. So if we know that the tunnel survives a fire, we also want to know, can we reopen it tomorrow, or actually does it take many months of repair works before we can again use the structure? So starting with the first part of the presentation is really a brief recap of things I've already presented in previous occasions. It's about how we actually model tunnels in fire, to model their structural fire response using SAFIR. So how do we do that? If you take a tunnel, which is a 3D geometry, that's a lot of work to model fully in 3D. So typically we simplify it by taking a 2D slice out of this tunnel geometry and modeling it as a 2D framework. So basically you see an example here. It's a tunnel in the Netherlands where we made such a slice and we divided it into different sections. So how does it work? Basically, every time there is a change in the geometry, can be either the width of the section or a change in the reinforcement. If the reinforcement on the cold side or the hot side is changing in the rebar area, we make a new cross section. So, and basically in that way, we can subdivide the entire tunnel into different sections and model its geometry and its properties in very much detail. After we have divided this tunnel into sections, the next step is to basically start doing our analysis in SAFIR. So first we do heat transfer analysis. So for each of these sections, we do a separate heat transfer analysis. And then using all those results, we put them together in a mechanical analysis where we apply the loads, we apply the boundary conditions, and then we see how does this tunnel behave in an actual fire. To illustrate this, I'm going to show an example. So again, this tunnel. It's a 2x4 lane tunnel, so actually quite a wide tunnel, but it's very different from a tunnel that you will find in the mountains. It's basically, you can almost call it a concrete box with a bit of soil on top. So it will behave very different from a circular cross-section tunnel, which is drilled throughout a rock face. In the analysis, we're going to look at the most severe fire case that we studied in this project, which is a 120-minute RWS fire, the Rijkswaterstaat curve. And where we also included a exponential cooling phase to basically extend the curve and to also study how this tunnel behaves during the cooling phase of a fire. So if we look at the heat transfer analysis, nothing too surprising there. Basically what we see is, if we look at how the temperatures change in the outer wall and in the roof slab, we see that at the fire exposed site, which is the blue curve, we see that it slowly increases, and then during the cooling phase, it starts to go down again. We reach temperatures of around 400, 500 degrees Celsius. And the reinforcement on the cold side, which is on the opposite side of the fire, actually remains cold throughout the entire fire. It's quite a hefty structure, and the temperatures do not penetrate all the way to the other side of the concrete cross sections. If we then take these results from the heat transfer analysis and we look at what happens on a structural level, basically we can, this is a typical view from SAFIR, we can plot the moment line. And I will now show in a short video how the moment line in such a tunnel can change if there is a fire in the left tube. So we see during the heating phase that this moment line moves upwards. So we get very large force redistributions, especially in the part of the roof slab above the inner walls. And we see that then during the cooling phase, this moment line moves back down again. I'll play the video again, and I'll draw your attention to the black arrows at the bottom. Those are basically the reaction forces, and you also see that those change throughout the fire as well. So during the heating phase, we get a very large increase in the inner wall, which is directly next to the fire, and then during the cooling phase, this force goes down again. To show this as a bunch of snapshots, I've made this slide. So basically on the left, you see the moment line at different points in time, again showing that the moments basically over the inner slab are increasing quite a lot during the fire and then going back down. And then if you look at the forces in the inner walls, we see that basically before the fire, these two inner walls are loaded more or less in the same way because we have a more or less symmetrical tunnel. And then during the fire, after 2 hours, we see that almost all these actual forces are being transferred to the wall, which is directly next to the fire. The wall, the other wall of the inner, the other inner wall, which is not exposed to fire, basically is almost fully unloaded. And then during the cooling phase, we see that things are settling down again, and that these forces are more or less equal again. So basically showing that in this tunnel, we get very large force redistributions in case of a fire. If you look at the deformations, so basically we plotted the deformations in the roof slab, which is under the fire. Then we see that during the heating phase, we get a very large deflection. Basically, the roof slab is moving downwards during the fire, but then also you see the dashed line after 2 hours, which is the start of the cooling phase. We see that the deformations keep increasing for almost 1 hour and only then start to slowly go back up. And we also see that after 24 hours of the fire, so basically we run the analysis for quite a long time so that the structure has time to really cool down. We see that we have a permanent deflection of around 57 millimeters. So if you look at the summary of this analysis, we see that in this case, for a 2-hour RWS fire, which is a very severe fire, we don't get the collapse, but we do get very large force redistributions, both in terms of the moments and also the actual forces. We get a lot of deformations, and also some of these deformations are permanent. And when we look at these results, we have some idea that probably this tunnel will also be quite damaged after a fire. It didn't collapse, but can we reopen it tomorrow or not? That is still a bit of an open question. So that brings me to the second part of the presentation, which is about post-fire damage. So briefly talking about our modeling approach, basically the first 2 steps are what I already discussed. We do heat transfer analysis and then a mechanical analysis. And then in the next step, we can also actually try to quantify what is the damage to the structure after fire. And even after that, also try to say something about, is it repairable or not? This last part is still under development, so I will not focus on that too much today. The main focus of this part is the damage analysis. So how do we do that? Basically, when you do a SAFIR analysis, you get a bunch of output files. You get thermal XML files, also temp files. And then from the mechanical analysis, you also get the mechanical XML files. We take all of those and we process them in our own Python script. And then from that, we get a bunch of more files. And today, I'm mainly going to focus on what I call the damage summary, where we basically bunch up all these results into one plot and visualize how the tunnel gets damaged during a fire. So I'm going to continue with the same example, again, of this tunnel with 2 × 4 lanes of traffic. And I will first show an overview of what our tool basically creates. So we see at the top, we see how the time is changing. So basically throughout the entire duration of the fire, both during the heating and the cooling, we can visualize what is happening to the tunnel. And then we have 4 quadrants, basically. On the right, we have the moment lines and the actual forces, which are exactly the same as the ones that you will get in diamond. But then on the left, on the upper left, we get the 300-degree isotherm, which you can use to actually say something about the repair works that are needed to the tunnel, because 300 degrees is typically what you use to say everything that was heated above 300 degrees, you have to remove and repair. And we can also quantify how much that is. But I think the most interesting graph is on the bottom left, is where we actually show where the cracks are forming and also formation of some plastic hinges. I'll zoom in on the graph on the upper left first, just to show you that you can quantify how much volume of concrete is being heated more than 300 degrees throughout the fire, and which can also tell us something about the cost of the repair works that are needed if we can repair it. But then more interestingly, if you look at the mechanical damage, we get the following plot. So basically, we have three colors. The gray color is basically concrete that is not cracked. So the concrete in that area has not been, has not reached any stress which was higher than the ultimate tensile stress of the concrete. And then we have the salmon color, so the light orange is basically where we are in the descending branch of the tensile model for concrete in SAFIR. So basically, as soon as we reach the maximum tensile strength and we're going into the descending branch, we can label it as lightly cracked. And then if the tensile strains are really high, we can actually reach a point where we go all the way to the end of the softening branch, and then we get what we call fully cracked concrete. And we can see in the animation how this is changing throughout time in this tunnel. Also interesting that you will see is those three red dots which we get. Those are what we call plastic hinges. At those locations, the moment line is changing to such an extent that actually the steel at the cold side of the tunnel is starting to yield. So you have the force distribution, the stress in the steel there is increasing. At some point, the steel stress is so high that actually it starts to yield, and we get the formation of what we call a plastic hinge. To illustrate this a bit further, I have these two graphs. On the left, we have the conditions before the fire. So you see the moment line before the fire, and also our damage analysis. You see some very light cracking, which is not uncommon for reinforced concrete structures. But then after 2 hours of fire, we see a completely different picture. We see that the moment line is different, and we see the formation of these three locations with plastic hinges. And these plastic hinges basically form because the moment lines are moving upwards. So you get higher negative moments in the roof slab and also in the outer wall. Also, interesting observation is that actually we also get damaged in the unexposed part of the tunnel, which is far away from the actual fire. It's only limited damage, but it is there. If we then also look on the graph at the bottom, you can see where we basically sum up the total length of sections which are cracked. In this case, after 2 hours, it's almost 40 meters. And if we then take the next slide, which is actually the damage after 24 hours of calculation, so actually at the end of the calculation, we see that this actually is still increasing. So during the cooling phase of the fire, we get some additional damage, which is forming in the structure. So now we have this tool. What can we do with it? Basically, what we could do in this case is we can look at the effect of passive fire protection. This tunnel today has no measures in terms of protecting it, so it's fully bare concrete. But the owner is actually looking to protect it because there's also some issues with spalling. So if we first look at the unprotected case, which is the one I presented before, we get again this graph, a lot of cracking, we get some plastic hinges. And now we can look, okay, what would happen if we would protect only the central part of the roof slabs? Because we get a lot of cracking in the roof slab, we get the plastic hinge. Maybe if we put some passive fire protection there, we can actually prevent it from happening. And if we do that, we see that we get a completely different result. We see that this cracking is severely reduced, and also the plastic hinge, which was in the roof slab, is no longer there. But you still see a plastic hinge in the outer wall, so we might have to do some additional works. A next step could be to actually protect the entire roof and the first meter of the walls. This is quite common in the Netherlands. And then we see if we look at this result, actually all the plastic hinges have disappeared. So actually the damage after the fire will be, again, a lot less than in the previous cases, but there is still some cracking. And then the last case, which you can also look at, is to actually fully protect it, just to see what would be the added benefit of that. And if we do that, we see that actually the result is almost identical as the previous case. So you can, from this already, conclude that actually protecting the entire tunnel, including the walls all the way to the bottom, will be costly, but it will not gain you a lot in terms of damage. Now, the case I presented up until now is for a 2-hour RWS fire, which is a very severe fire. The client also asked us to look what would happen in case of a smaller fire, because not every fire is as severe as a 2-hour RWS fire. So for that, we also did an analysis of a smaller fire. So basically, we got some CFD results, and we translated them in a very simplistic way to a bunch of time temperature curves. You see that the temperatures in this case are much lower than an RWS curve fire. We have maximum of 700 degrees, and it's only in the central part of the roof slab. But actually, if we run the analysis, we see that after this 2-hour fire scenario, still we get quite high damage. So even in a small fire, we still get, in the case of this tunnel, we get plastic hinges and some severe cracking. So to summarize this case study, basically we see that as of today, there is no plastic fire protection, and if there would be a fire, either a severe one or a small one, there would be cracking and formation of plastic hinges. If we protect the roof and the first meters of the wall, which is quite common in the Netherlands, this would already be severely reduced, but there would still be some damage and some cracks. And as I said, in case of a small fire, there will still be some damage. I will quickly also go towards a second example, which is another tunnel we also studied. It's basically a tunnel with two levels of traffic. There's 2 times 2 lanes of traffic stacked on top of each other. And this tunnel, as of today, is already protected. So there is protection on the roof slab and also the first meter of the walls. If we then consider the case of a fire in the upper tube, and we look at the 300-degree isotherm, we see that that the passive fire protection is working quite well. We see actually that the entire roof slab and also the first meter of the walls remains relatively cold, and there's no region where actually you get the concrete exceeding 300 degrees Celsius. So in that sense, you can see that also in our post-processing, this passive fire protection is clearly being visualized. If we then look at the damage, we can again try to plot the cracks and plastic hinges. We see that initially during the fire, this is very limited. There is some cracking, but not too severe. And then after about 1 hour and a half, so 90 minutes into the fire, we get a plastic hinge in the inner wall. That's an area which is not protected, so it's not too surprising. But it was nonetheless interesting to see that even though there have been taken some measures to protect the structure, we can get damage in the form of a plastic hinge in this tunnel. And again, even though this tunnel is being protected with passive fire protection, we get large force redistributions, and because of that, you can have the formation of these cracks and plastic hinges. Then, as a last case, we took the same tunnel, but we had fire in the bottom tube, and then we get a very different view. Again, at the beginning, cracking is very limited, but then at some point, not during heating phase, but actually during the cooling phase, we see the formation of a plastic hinge all the way on the outer edge of the intermediate slab after about 3 hours, I think. So if you wait a little longer, we see that the moment line again is moving upwards, and then at some point we get the plastic hinge in the intermediate slab of this tunnel. So to summarize this case, basically we get large force redistributions despite the fact that there is passive fire protection. We get plastic hinges again, despite the fact that there is passive fire protection, and the location of the damage clearly also depends on the location of the fire. If there is fire in the upper tube, you have a completely different damage image than if there is fire in the bottom tube. So that brings me to the conclusions. So we developed a damage analysis tool because really there was a question from our client like, okay, it's nice to know that our tunnel does not collapse in case of a fire, but what to do after? What will be the damage? Can we repair it? So basically, it's a tool which can help us to quantify and also visualize this post-fire damage. And it can also actually help in the design of passive fire protection. And it demonstrates that even though if you have a tunnel with passive fire protection, or in case of a small fire, there can be quite severe damage. And it can also inform repairability analysis. So the next step for us is now to actually help the clients, informing them on how we can quantify the repairability of such a tunnel. They also have some considerations where a tunnel which is underwater has possibly higher different targets than a tunnel which is under the land, where you can just remove the soil and then do some repair works. If the tunnel is underwater, that's not possible. And then repairability is for us actually still a bit of an open research question. We have seen that Thomas has published a paper about it in concrete buildings, but actually for tunnels, there are some additional questions that we need to answer. If you're talking about thermal damage, you can use the 300-degree isotherm. We can directly get it from SAFIR. Also, the residual deformations, we can get some information there as well. But this formation of these plastic hinges and these areas with very large cracks, I think, can also be a metric to decide whether or not a tunnel is repairable or not. And that's something which we are still looking into today. So that was my presentation, and I'm now available to answer all the questions.